Okay, welcome everybody. I'm going to take you on a bit of a guided tour through some lovely examples and stories from the world of enumerative geometry. I'll give you some idea of the kinds of questions that we like to ask and the kind of techniques that we use to find answers to those questions. So we'll begin with the circles of Apollonius. So the story here begins, as many stories do, in the year 218 BC. So at this point, the Roman Republic is in ascendance. It's taken control of most of Italy, and it's coming into contact with the Carthaginians, who at that time were the dominant superpower in the region. So the Carthaginians are based in Carthage, so Tunis nowadays, in Tunisia. And they're a Phoenician civilization, so they descend from traders who originated in Lebanon with an extremely rich material culture. The Phoenician alphabet is the basis for most writing systems in use in sort of Europe and the Middle East, to this day. The Carthaginians are somewhat perturbed by this sort of upstart entity called the Roman, Republic that's starting to threaten its possessions. So there were a series of wars that were fought between the two powers. And what's going on here, this is in the Second Punic War, so the second of these wars. And this strapping fellow dead center is the Carthaginian general Hannibal. And what he's doing is he's leading his army, including many of his war elephants, across the Alps, so from Spain into Italy. And his sight is set on Rome. And this is obviously a 19th century engraving and perhaps a little bit embellished. If you look closely, you will see a elephant falling off the cliff in the background, which I found quite amusing. But after this, so Hannibal would conquer most of Italy, but he wouldn't conquer Rome. He wasn't quite able to do that. People debate whether that was due to structural reasons or whether there was just mistakes that he made. And in the end, Rome defeated Carthage, and in the Third Punic War, actually, they burned the city to the ground and established, their dominance over the Mediterranean. And if they hadn't, things might have turned out differently. Okay, so this is happening in the Western Mediterranean. At the other end of the Mediterranean, there was someone called Apollonius of Perga, who was living in what is now Turkey. And he was thinking about something maybe a little bit less exciting than leading his elephants across the Alps. So he was thinking about the following problem. Let's choose 3 circles. So here they are in red. And I'll just pick them sort of at random. And I want to ask the following question. How many circles can I find that are tangent to all 3 of these? So here's an example. So this blue circle, if you see, will meet each of the red circles in one point, and it meets it with some sort of tangency order, right? And if you look a bit closely, what you'll notice is that the blue circle is sort of inside this large red circle and is sort of outside the 2 smaller red circles at the bottom. Okay, let's look at another example. So once again, this blue circle is sort of tangent to all 3 of the red circles. And here now, if you look closely, you'll see that it's sort of inside both this red circle at the top and this red circle at the bottom right. And it's sort of outside this red circle on the left. So trying to extrapolate from this, we might guess the following. For each of the red circles, I'm going to sort of choose whether I want to be inside or outside. And then once I make those choices, I'm going to conjecture there's a unique blue circle tangent to all 3 with those properties. And indeed, the answer turns out to be yes, there is. So here goes. If we count them up, we've got 1, 2, 3, 4, 5, 6, 7, 8 blue circles, right? And each of them is sort of inside some of the red circles and outside some of the other, and they're all tangent to the 3 red circles, right? So obviously I got the number 8 here because I had to make sort of 3 binary choices. So 2 times 2 times 2, I get the number 8. And it turns out in this case that these are the only circles that are tangent to these 3 red circles, okay? So we started off with that question, can we find all of these blue circles? And in the end, we ended up with an answer. And the answer was like, yes, not only can I find them, but I can tell you how many there are. In this case, there's 8 of them. Okay, So this is sort of the prototype of a enumerative geometry problem. And there's a couple of general lessons that we can extract from this. So the first is kind of, we sort of had it implicitly, but we didn't really remark upon it, is this fact that we really only got a finite number of these blue circles. And that wasn't obvious from the way I set up the problem, right? I gave you these red circles. I said, I want to look at all the blue circles that are tangent to them. And it wasn't really obvious that I should get a finite number, right? I could have got infinitely many. And then I wouldn't be able to write something as sort of satisfying as the number 8 as the answer to my problem. So that's kind of the first lesson. The second lesson is that this number that we get, this number 8, doesn't really depend on the 3 red circles that we started with. So I kind of chose these 3, right? And I just sort of said, well, I'll choose them randomly. Of course, I could have chosen, a different collection of 3 red circles. But if I'd done that, it turns out that as long as I chose those 3 red circles kind of generically, as long as I chose them sort of reasonably, I would still get this same number 8 as my answer. So what this is suggesting is that this number is not just some sort of random, meaningless number. It's actually reflecting something deep about the geometry, something so deep that it's sort of insensitive to moving around these red circles a little bit. So both of these lessons kind of form the bedrock for enumerative geometry. They're kind of the mortar that the whole subject is built out of. And as we'll see later on, both of them can be kind of explained by a slogan. And that slogan is going to be intersection theory on moduli spaces. So we'll see how that goes soon. All right, so coming back to the original problem, I started with these 3 red circles, right? And you might ask, well, why 3? Why didn't I start with 4 red circles or 5 or 1 or 2? Well, let's try it out and see what happens. So let's first think about what would have happened if I had 4 red circles. Well, we've already seen that if I have 3 red circles, then I only have finitely many of these blue circles that are tangent to all 3. So if I now introduce a 4th red circle, right, let's say I just drew it sort of randomly in this picture, you can sort of see that it won't be tangent to any of the blue circles that I've chosen. And what that means is you won't be able to find any circle that's tangent to all 4 of the red circles. So if I'd started with 4, the answer I would get, the number of circles I would get would just be 0. I wouldn't be able to find any. Okay? So 4 is sort of asking too much. What about 2? Well, it turns out that 2 is sort of asking too little. So if I just picked 2 of these red circles, let's say this one up here and this one down here, then what I would be able to do is I could basically squeeze infinitely many blue circles into this gap in between them, okay? So I could just take this blue circle here and sort of shift it over to the right, sort of roll it over and squeeze it into the corner, and I would have another circle which is tangent to both. So it turns out that if you take only 2 red circles, then you're going to get infinitely many of these blue circles that are tangent to your 2 red circles, okay? So 4 is too much, asking too much. 2 is sort of asking too little, and 3 is just right. Okay, it's the Goldilocks zone. So let's try to understand why that is now in a more conceptual way. So let's say I want to give you a circle, right? So what data, what information do I have to convey? Well, I have to tell you basically 2 things, right? I have to tell you the center of the circle, so I can give you its coordinates A and B, and I have to tell you the radius of the circle, right? Some positive real number. And so what we could say is we could say that the space of circles, right, is given by this product. So R2 cross R positive, right? So that means that if I give you any point in this set, that corresponds to some circle and vice versa. So this word moduli space essentially means that. It's some space where the points in it correspond to some geometric object that you want to parameterize. In this case, it's the circles. And if we look at this space, what we notice is that there's sort of 3 independent parameters, right? There's the coordinates for the center, A and B, and then there's the radius, R. And what that means is that this space is sort of 3-dimensional, right? I have to give you a circle, I have sort of 3 degrees of freedom. And if you give me one circle, there's kind of 3 different ways that I can start deforming it to other circles. I can sort of shift it in the horizontal direction, I can shift it in the vertical direction, or I can sort of shrink it and grow it. And that will correspond to kind of wiggling around these 3 parameters here. So the dimension of the space of circles is 3. It has 3 independent parameters. And now what are we doing with this problem with the tangencies? Well, we're fixing some circle and we're imposing tangency to it, right? So every time that I say that I only want to look at those circles tangent to my given circle, I'm cutting down this space of circles. I'm going to something smaller. And every time I do this, I'm cutting down the dimension by 1, okay? And for this reason, 3 is the sweet spot. So if I impose tangency to 3 circles, then I go from a 3-dimensional space, first to a 2-dimensional space, then to a 1-dimensional space, and finally to a 0-dimensional space. Well, what is a 0-dimensional space? Well, it's a collection of points, right? And once I have a collection of points, I can count it. I can ask how many there are. So this is why 3 is this sort of Goldilocks zone. This is why 3 was the right number to look at from the beginning. And later on, we're going to develop some more elaborate ideas to show that really there are exactly 8 of these circles. Okay, so let's fast forward from the Punic Wars between Carthage and Rome. We're now going to go into I guess either 19th century Europe or potentially sort of 12th century Baghdad, depending on how you interpret things. But we're looking at algebraic equations now. So our starting point will be the plane, right? So we're all happy with the coordinate plane with coordinates x and y. And something that probably everyone remembers in school, a lot of people don't remember it very fondly, is the theory of conic sections, right? So I can give you some quadratic equations. So here it is. There's 1, 2, 3, 4, 5, 6 different terms appearing, right? And the coefficients A, B, C, D, E, and F. And we know that sort of the vanishing set to such an equation gives us a conic section, right? And there's a classification of them. So I stole this from Wikipedia. Right, so there's basically 4 types of conic sections, so circles, ellipses, parabolas, and hyperbolas. And you'll see that I've sort of crossed out the circle because I think that a circle is just an ellipse that can't face reality. So for me, there's not really a big distinction between circles and ellipse, but these 3 really are quite different, right? So I have ellipses, parabolas, and hyperbolas. All right, so we have this kind of taxonomy, and that's all well and good, and we know that we know that this taxonomy has something to do with the shapes of these equations and the positivity or negativity of these coefficients. So now we're going to ask the following question. I'm going to take 2 conics and I'm going to kind of lay them on top of each other, okay? And then I'm going to ask the following question: what happens when I do this? So here I've got my options, horizontal and vertical. And here's the first case. So I overlay 2 ellipses, and you'll notice that they're sort of meeting in 4 points here. Okay, all right, that's kind of interesting. So here's an ellipse and a parabola. And again, if we count it up carefully, I've got 1, 2, 3, 4 points that they're meeting. All right, let's keep going. Okay, so you can see that something has happened, right? So for any sort of choice of, conic and conic, I overlaid them, and in every single case, you see that I'm getting these 4 points, right? So the question is, where does this number 4 come from? Okay, obviously these are conics. They're defined by degree 2 equations. So obviously the number 2 is going to sort of play a role here. But 2 is kind of a small number. And because of that, it's kind of unclear whether I should interpret this 4, like should it be sort of 2 plus 2, like the degrees of the 2 conics, or maybe it should be 2 times 2, or maybe it should be 2 to the power 2. It's not quite clear at the moment. This is mathematics. In order to spot patterns, we do more examples, right? So let's do some higher degree examples. So here what I've done is I've taken a cubic, right? That's in green, and I've intersected it with a conic, that's in red, and we count up 6 points, okay? So that's the degree of the cubic times the degree of the conic, okay? Here's a cubic and a cubic, right? So here we're getting 9 points, we can count them up. Let's just do one more just to be sure. So here we've got a quartic in green, right? And a cubic in red. And again, if we count up all the points, we've got 12 appearing, okay? So it seems that this is sort of multiplicative, right? We multiply the degrees and we get the number of points. And actually, if you kind of think about it conceptually, it also sort of makes sense. So this quartic is sort of making 4 passes in the vertical direction because it's a quartic. So it's sort of 1, 2, 3, and 4. And the cubic is sort of making 3 passes, 1, 2, and 3. And so we get this kind of, checkerboard pattern. And it kind of seems to really be giving us the number of intersection points, the number of points where these meet. All right, so we've noticed the pattern, and we can make some general hypothesis, right? So if I give you some 2 curves in R2 with some fixed degrees, D1 and D2, right? So the equations defining them have degrees D1 and D2, then we can guess that the number of intersection points is precisely the product, right? d1, d2. Okay, so everything seems good so far, except not quite. So I swindled you a little bit here. So we're back in our conic case, right? So we've got two conics overlapping, and we can see they're meeting in 4 points. Everything's good. But of course, what I could do now is I could take this red conic, let's say, and sort of shift it over to the right a little bit, right? And at some point, what's going to happen is I'm going to get a picture like this, okay? So now they're no longer meeting in 4 points, of course, they're meeting in 3 points. But this is actually not so bad because you could imagine that, okay, whereas while they're only meeting in 3 points, this third point here is sort of should sort of count twice because it has some tangency, it has some multiplicity. So maybe you could imagine that you could make sense of this as counting for 4 points still. But of course, what you can't make sense of, at least at the moment, is the following, which is if I keep pushing it over to the right, now I just got 2 points, and these definitely only have multiplicity 1. So it seems like I've just lost 2 points. They've fallen off the face of the earth. Okay, so what's going on here? Well, let's think a bit more abstractly about what we're doing, right? So we've got these curves, and they're defined by some equations, f1 and f2, right? These are polynomial equations. And what we're doing when we're finding these points is we're solving some system of simultaneous polynomial equations, okay? And we know that when we're solving polynomial equations, if we want some consistent answer, if we want a predictable answer, then we should really be working over the complex numbers, okay? So we shouldn't be working over the reals, we should be working over the complex. So that's what we're going to do. So we're going to replace R2 by C2, okay? And we'll think of our curves as living inside C2. Okay, now this requires a leap of imagination because I can't actually draw C2. So what I'm going to do is I'm going to continue to draw the pictures as if they're happening over the real numbers. But we just have to bear in mind that this isn't going to always be an accurate drawing. And really what I'm drawing is just the real locus of some curve in C2. Okay, so let's kind of set that up. So we have now, just like before, curves C1 and C2, but now they're living in the complex plane, right? So C2 with coordinates X and Y. And, you know, they're still defined by some polynomial equations, the same polynomial equations that we had before, and those have some degree, okay? And now we kind of guess that maybe this is the right approach, okay? So in the previous picture, what would have happened here, as I went from having 4 points to 2 points, is that these kind of 2 points that I'm losing, they're still sort of there, but they're just living in the complex world, okay? So I don't see them in the real plane, but they are still there. They're just living in the complex plane now, okay? So this is our guess that we still have this D1, D2. And this is a lot closer to the right answer. But it's not quite it's not quite right. It's still not quite right. So I was messing with you again. And to see why I was messing with you, we can actually see this in the simplest possible case. So let's look at degree 1 curves. So C1 and C2 are both lines, okay? And I'm going to look at the case where these lines are parallel, right? So they're defined by some equation here, maybe x equals 1 and x equals 2, right? So that's 2 lines parallel to the y-axis. And what you see here from our guess, right, we would expect that these meet in, well, the degree times d1 times the degree d2 points, and in this case both degrees are 1, so we expect this to be meeting in 1 times 1 points, which is so 1 point. But actually these parallel lines don't meet at all, okay? And this is nothing to do with working over the real numbers or working over the complex numbers. They just never meet basically over any field, because this solution, this equation x equals 1, x equals 2 has no solution. Okay, you can't have x simultaneously being 1 and 2. Okay. All right, so this is a bit disappointing because it means that our guess, our sort of improved guess, still doesn't quite work. But that's okay. There's a fix. So this is a kind of really a cliche at this point, but it really is the best way to drive home the intuition. So we're looking at a railway track, obviously, and we've got these kind of parallel rails. And as we look off into the distance, we sort of see that they're getting closer and closer, right? And maybe this isn't a great example because I've got trees here, but if we could imagine going off to the horizon, maybe I've illustrated it better on this side, we could imagine those rails converging to some point, okay? And this is the basic idea behind projective geometry. So what we're going to do is we're going to, just like we extended from R2 to C2, we're now going to extend from C2 to something called the projective plane. And the way we'll do this is by adding a horizon to this C2. So we think of these as some points at infinity, and they correspond to some sort of asymptotic direction. So as a curve goes off to infinity, in the limit, it has some sort of limiting direction, and there'll be new points living at infinity that kind of keep track of that direction, okay? So we call this the projective plane, and we write it P2, so P for projective. So it's C2, the normal thing, plus these kind of points at infinity. And for those of you who have done some topology, the thing that's interesting about P2, which distinguishes it from C2, is that it's compact. Okay, so don't worry if you don't know what that means. So if I have a curve in C2 defined by one of these polynomial equations like we were looking at, then I can get a new curve. We'll write it C bar in P2, okay? And the way that that works is I take my original curve in P2 and then I just add a few more of these points at infinity. And the ones I add in kind of correspond to whichever asymptotic directions I see in this curve, okay? And by doing this, we can finally fill in all the missing pieces. So those two lines that we had before now do meet in a point. It's just that point is living in infinity. And more generally, we have the following, which is a really tremendous achievement of 19th century algebraic geometry. This is Bezout's theorem, okay? So it says that we start with two curves in P2 of some degree, D1 and D2. And then the number of their intersection points is D1 times D2, always, okay? So, so this is a wonderful theorem. And in a way, you can think of this as a generalization of the fundamental theorem of algebra. Okay, so it's sort of saying it's counting the number of solutions, not now to just a single polynomial, but to some system, some simultaneous system of polynomial equations. Okay. One proof of this, maybe the classical proof, uses a lot of sort of interesting, basically algebra of polynomials, so homogeneous polynomials, resultants, things like that. But we'll see another proof, or at least the idea for another proof, a bit later on. Okay. So we went on a bit of a journey here, right? So we were trying to find the number of these points, and basically what we found was that in order to sort of get a predictable answer, right? So in order to get a theorem that we could just state in one line, we had to kind of perform these extensions, right? So we had to go from sort of R2 to C2, right? Working over the complex numbers, and then we had to go from C2 to kind of this projective plane P2 by adding these points at infinity, okay? So obviously the benefits of doing that is that we could get a statement that just applied to all curves at once, okay? So we didn't need to kind of distinguish between different types of curves. Actually, when we work over C2 or P2, this kind of taxonomy of conic sections kind of breaks down. So actually, over the complex numbers, all conics kind of look exactly the same. You don't get this distinction anymore between parabolas and hyperbolas and ellipses and so on. So this is a benefit, okay, in a way, because it's more uniform. You can make statements that apply, globally. But of course, you pay something, and what you pay is that your statements are more uniform, right? So you lose some of the richness that existed previously, whether you view that as a benefit or a drawback kind of maybe depends on your personality, or maybe just depends on your mood on any given day, okay? But I will say that even if you're interested in, for example, studying curves over the real numbers, so even if you view this extension more as a drawback than a benefit, nowadays when people are studying these things over the real numbers, they still sort of tend to work over the complex numbers and then sort of look at things that are basically invariant under complex conjugation. Okay, so it's a bit like if you're studying solutions of polynomials over the reals, it helps to know that there are solutions to polynomials over the complex numbers and that these come in complex conjugate pairs and so on, even if you don't really want to find those at the end of the day. Okay, so so this is just something to bear in mind. Uniformity isn't always bad. All right, so here's Bezout's theorem again. And okay, we kind of arrived at it through some fairly concrete calculations, but I also just want to take a moment to just reflect on it a bit more abstractly. So if we look at this theorem, something you'll notice immediately, right, is that this number, D1, D2, this final answer that we get on the right-hand side, it doesn't really depend that much on the curves C1 and C2, right? It only depends on them through their degrees, okay? So what that means is if I start with some curves C1 and C2, and then I start deforming them a little bit, if I start kind of shifting them around or stretching them and squeezing them, this number that I get isn't going to change, okay? So it's unchanged under what we would call deformations of C1 and C2, okay? So what this really means is, C1 is defined by some equation, and I could start to just vary the coefficients of that equation in some way. And when I do that, my C1 will kind of morph in some way, but this number, this intersection number, won't change. Okay, so it's really something that's quite intrinsic to just the fact that my curve had some fixed degree. Okay, so this may be reminiscent of what we saw with the circles of Apollonius at the beginning. Okay, so what this suggests is that we should maybe study curves in P2 only up to sort of these deformations, right? So only up to whether I can deform one curve into another. And this leads to the theory of Chow homology, okay? So there's this thing called, don't worry too much about what A1 means. It just means one-dimensional cycles. So A1 of P2, and what this is it's the set of, we're going to define this. This is called the Chow homology of P2. It's the set of curves up to deformation. So again, deformation means, you have your curve defined by some polynomial, and then you start sort of deforming that polynomial. You start varying the coefficients of that polynomial, and your curve kind of starts to, move around or stretch and squeeze in some way, okay? And it turns out that this set is actually very easy to describe. It's just the set of non-zero natural numbers. Okay, so a curve, in other words, if I have two curves of the same degree, right? So that's what these numbers here are recording. They're recording the degree of this curve. Then I can deform one to the other by sort of changing the coefficients of the polynomials. Okay, so in this world, we can make sense of things like Bezout's theorem, right? If I give you a curve, it defines some sort of equivalence class, which is just some element of this set, which only really records the degree of that curve, and we can make sense of Bezout's theorem in this kind of world, in this very restricted world where we've sort of quotiented by this very large equivalence relation. All right, so we'll say more about this in a minute, but before we do, I just want to tell you a little bit about Chow, who was the person who really, if my history is correct, proved the sort of main result that allowed for the definition of this. So Chow had a very interesting life. So he was born in 1911 to a sort of upper middle class family in Shanghai. And he was born at a very turbulent time in Chinese history. So a few weeks after he was born, the Qing dynasty was overthrown in a revolution, the 1911 revolution in China. And that ended sort of 2,000 years of Chinese imperial history, basically. And it was replaced by a republic, which went through various kind of coups and periods of, I guess, what is called warlordism, but basically civil wars. And eventually it was, sort of taken over by the Kuomintang in the 20s, and then finally by the Chinese Communist Party in the 40s. But Chow he was educated for some of his life in the United States, but he studied for his doctorate in Germany. So he went to Göttingen, and he was there. It was there that he met the woman who became his wife, who was a German, Margot, I think was her name. So he wrote his thesis, and he was spending time in Göttingen, in Hamburg, in Leipzig. But this was in the 1930s, and obviously with the Nazis coming to power in 1933, after a few years, he stayed, I think, until 1936 or so, but his position basically became untenable. And so together with his German wife, they left and they went back to he returned to China. And he arrived in Shanghai just in time for the Japanese invasion in 1937. So it wasn't a great decade for him. And although he'd proved some remarkable results in his thesis, and he continued a little bit when he'd returned to China, pretty soon with the sort of the conditions of the war being what they were, he wasn't really able to continue with his mathematics. So he sort of went silent for about 10 years. And then after the war, the great Chinese mathematician Chen, who had known Chow in Germany, sort of gave him the opportunity to come to the US, and he was very instrumental in building the algebraic geometry group at Johns Hopkins University in Baltimore, which is where he stayed for the rest of his life. So yeah, very interesting individual, and he made a lot of amazing contributions to geometry. One of which is the theory of Chow homology, which for me I use every single day in my in my research. So anyway, back to mathematics. We've got this idea that we want to look at curves up to some notion, so this notion of deformation. So there's these equivalence classes, and basically from, if we do this, the only information we really retain about the curve is its degree, okay? So at the moment, this is just some sort of set, but we can do a bit better than that. So what we notice is that, for example, I can start with a conic, right, which is supposed to correspond to the sort of 2 in this set, and I can deform it to a union of 2 lines, okay? So the way I do that is, so the equation of this union of 2 lines is actually the product of the 2 linear equations defining the 2 lines. So you can do that as a little exercise for yourself. So convince yourself that if this is defined by some linear equation and this is defined by another linear equation, then their union is defined by the product, okay? So when I expand out that product, I get a degree 2 equation, right? And I can view that degree 2 equation as coming from a conic by kind of deforming and degenerating the coefficients in some way. So I can deform this conic to a union of 2 lines. And what I notice is that 2, which was the conic's degree, is sort of 1 plus 1. Okay, go figure. It's not particularly surprising. But what this suggests is that there should be some geometric interpretation for this. Which is that this set, this Chow homology, isn't just a set. It has some algebraic structure given by union. So if I take 2 curves, I can take their union, and this kind of respects these deformation classes. Okay, so I get some notion of addition on this set, which is just the usual addition, if I view it this way, of natural numbers. Okay, so I have this addition given by union. But it turns out that there's another algebraic structure on this set. So not just addition, there's also a scalar product. So I can take 2 elements here and take their product and get a number. And that number is the number of intersection points, okay? And so this turns out to be well-defined. It's not obvious that it is. You have to kind of argue that things are well-defined up to deformation. And again, if my history is correct, I think this was one of Chow's main contributions, was to sort of argue that this is actually well-defined, okay? So we have these algebraic structures, addition and scalar product, and Bezout's theorem tells us that the kind of the product on here is just sort of the usual product, right? So like 2 times 4 should be 8 because they intersect in 8 points, okay? But that's not really that's not by definition, that's a consequence of Bezout's theorem. Okay, so when we have some algebraic structures, we can start to ask what sort of axioms they satisfy. And these ones will satisfy all the usual axioms you expect. And in particular, and you can check this as an exercise, these are distributive. Okay, so addition will distribute over multiplication here. So let's take that on trust. Let's see what we can deduce. We're going to give a new proof of Bezout's theorem. Well, we didn't give the old proof, but I'm going to give you a proof now of Bezout's theorem. So here's what I'm going to do, right? So I start with my C1 and my C2, and they have, degrees D1 and D2. And what I'm going to do is I'm going to degenerate them to a union of lines. So here's my example. So I've got a cubic, right? And a cubic will degenerate to 3 lines because a product of 3 linear equations is a cubic equation. So 3 degenerates to 1 plus 1 plus 1. And similarly, I have a conic, and it degenerates to 1 plus 1 like we saw before. And now what I can do, right, is because we know the intersection is well-defined, up to deformation, I can now perform the intersection here on this kind of degenerate, on this degenerate object. And so here's the picture I get, right? So I just superimpose these 2 lines. And if you count up, okay, we can count up, obviously, we can count that there's 6 intersection points. But more than that, we can do it kind of algebraically, right? So the operation that I've used here is precisely the distribution of addition over multiplication, right? So 1 plus 1 plus 1 times 1 plus 1 is 1 times 1 plus 1 times 1 and so on, right? And you count it up and there's exactly 6 of them, which is what we expected, right? It's 3 times 2. That's the number of intersection points that Bezout's theorem would give us. So this might look like I'm kind of swindling you here a little bit, but I'm really not. So the only input we're using here is the fact that these intersections are, well-defined, invariant under deformation. The fact that this operation is distributive, and then there's kind of like a base case for the induction, which is that 2 lines intersect in 1 point, right? So 1 times 1 should give me 1 because 2 lines intersect in 1 point. And from that basic fact, which is kind of like an axiom of projective geometry, we'll see that later on. from the fact that two lines intersect in one point, we've deduced Bezout's theorem using basically this deformation argument. And I'll just mention that this isn't something I've just kind of cooked up for you now. This general philosophy that you can prove things about complicated things by degenerating them into unions of simpler things and using what you understand about those simpler things. This is a completely ubiquitous technique in research up to this very day. Okay, so people use this kind of stuff all the time. Okay, so we understood Bezout's theorem, and we'll come back to it soon. But let's kind of change tack a little bit and talk about the moduli space of lines. Okay, so we're going to come back to these moduli spaces that I briefly mentioned at the beginning. So what is a moduli space? So it's some space whose points should correspond to some sort of geometric object that we want to parameterize. Okay, so I'll give you an example. So we'll look at C3 and we'll view it as a complex vector space. Okay, so a three-dimensional complex vector space. And what I want to look at is one-dimensional vector subspaces. Okay, so we think of these as lines. I mean, they're complex one-dimensional lines. And okay, they're vector subspaces. So I guess if you like, they're lines passing through the origin. Okay, so one-dimensional subspaces of C3. And what I want to do is I want to parameterize those. So I want to find some space whose points correspond to those one-dimensional subspaces. So in order to do that, I have to kind of think about the information that I'm recording here. So what information do I have to give you one of these subspaces? Well, every one-dimensional subspace can be written as being generated by a single vector, V, right? And that vector it can be any element of C3 except for the zero element, right? Because if I take the zero element, I won't get a one-dimensional subspace, I'll get a zero-dimensional subspace. But other than that, any non-zero element is fine. So I can take V to be any non-zero element. And moreover, this V is sort of unique. It's unique up to multiplication by C star, right? So if V and sort of 2 times V will give me the same subspace. But as long as, if I have two vectors that don't differ by an element of C star, then they'll genuinely give me different subspaces, okay? And so what that means is that the sort of moduli space of lines in C3, right? So the space of all these lines that we want to parameterize can be expressed as follows. So I take sort of C3 minus the origin, so my sort of space of V's, and then I quotient by C star. So that means I identify two V's if they differ by multiplication by C star. Okay, so there's this quotient here. So here we have it again. Okay, so this is something that, I mean, it seems okay, we could sort of try to think about this, but I claim actually that this is something we've already seen. So the claim is that actually this quotient is nothing more than this projective plane P2 that we already saw. So I remind you, that was C2 together with these sort of points at infinity, yeah, these asymptotic directions that we added in. All right, so let's give a proof by picture. So I need some way. So remember, this set on the left is kind of parameterizing one-dimensional subspaces of C3, and I need some way to go from sort of elements of the left-hand set to elements of the right-hand set. So if I have a line in C3, again, I'm drawing this kind of really in R3, but you can use your leap of imagination. If I have a line in C3, I can see what happens when it intersects this plane at height 1. Yeah, so here there's the origin, and I'm going to take the third coordinate and look at where it's equal to 1. So that's some sort of plane translated upwards at height 1. And if I have a line, like let's say this red line here, I can look at where it meets this plane. Okay. Now, this plane itself is just a copy of C2, right? Because I've fixed Z3 and then Z1 and Z2 are kind of free parameters. So this is a copy of C2. And if I look at this intersection point, I get a point of C2, yeah? So to every line dotted here, here's one, here's another, I get some point of C2, and those will correspond to the points of C2 here, yeah? So I go from some line on the left to some point of C2. Okay, so that looks like a pretty good correspondence, and obviously I can go the other way, right? If I give you a point in C2, let's say this one here, I can just draw the line from that point to the origin, and I get one of these vector subspaces, one of these lines in C3, okay? So that seems good, but I've missed out something, right? Because there should also be these points at infinity. So what have I missed out? Well, not every line in C3 is going to meet this plane, right? There's some that don't, and those are the ones that are purely horizontal, right? So these green lines here, because they're sort of living in the parallel plane to this Z3 equals 1, they're never going to meet this plane, okay? So what do these correspond to? Well, let's think about it. They sort of correspond to directions in C2, right? These are lines going off in C2, which is this plane down here, and they correspond to sort of asymptotic directions. And so these correspond precisely to these points at infinity, right, which were supposed to be the asymptotic directions of my C2. So in this way, I get some correspondence between these subspaces here and the points here, yeah? And I interpret it as a point of C2 if it's not in this sort of Z3 equals 0 plane, and otherwise I interpret it as a point at infinity by thinking of these asymptotic directions. So the conclusion here is that P2, this space that we kind of introduced at the beginning, right, using these ideas from projective geometry, I can actually think of it as a moduli space, meaning that every point in P2 corresponds to some geometric object, which in this case is these lines in C3, so these one-dimensional vector subspaces of C3. Okay, so here's just that here's that stated again. Yeah, so in P2 on the left-hand side, I just have basically this space of one-dimensional subspaces. Okay, so now that we've set this up, we can now start to do some linear algebra, and we're going to deduce something quite interesting about P2 that we didn't know before. So let's forget about P2 for a minute. Let's just think about, linear algebra. If I give you a one-dimensional subspace of C3, something you can do is you can find the perpendicular, right? So you use the sort of inner product on C3, and you can build a perpendicular subspace. And since C3 is three-dimensional and W is one-dimensional, this perpendicular thing will be two-dimensional. Yeah. So to every W, I get a H, which is this perpendicular subspace. Okay. Well, that's fine. But now we've just said, right, that W should correspond to some point of P2. Okay. So that means that to every point of P2, I get some W, and then to that W, I get this perpendicular subspace. Now, what does that subspace correspond to in the P2 world? Well, if you think about it, so a two-dimensional subspace of C3, you can sort of think about it as a union of one-dimensional subspaces, right? So I can kind of cover it by one-dimensional subspaces, and then my H is just some union of these one-dimensional things. So that means that it's basically a union of points in P2. And what kind of union is it? Well, it turns out actually to correspond to a line in P2. Okay, so just as one-dimensional things corresponded to zero-dimensional things in P2, two-dimensional things here correspond to one-dimensional things in P2. Yes, so the dimension kind of drops by one each time. And so summarizing, what we see is that if I have a point in P2, I can kind of follow this diagram around, and what I end up with is a line in P2. Okay, and this correspondence is known as projective duality. So the way that I think about this is that I have some point in P2, and then I have some line in P2, which is sort of opposite to my point in some way. Okay, so in the C3 world, it's orthogonal, it's perpendicular, and in the P2 world, it's sort of sitting opposite it somehow. It's sort of facing, across the whole landscape of P2. It's sitting right at the other end. Okay, and I can go back and forth between these two things. So projective duality is tremendously powerful, and we'll see examples where it can be used in a minute. But there's another way so we've sort of understood this algebraically, right, by thinking about subspaces and how we parameterize them and so on. But there's a different way we can understand projective duality, which is much older in a way, and that's this axiomatic approach. So let me just talk about this a little bit, because I think this is quite fun. So we set up projective geometry as saying that there's some, set P2, and it has this interpretation, and I can look at, polynomial equations and so on. But there's a different way we can do projective geometry, which is to start with some very, very simple sort of bits of information, which is just the following. So I have some set of points, I'll call it P. I have some set of lines, I call it L. And then I have some incidence relation I. So here what we mean is that kind of, P comma L belongs to I if and only if P is an element of L. Yeah, so this incidence relation is basically just recording which points belong to which lines and which points don't belong to which lines, okay? So this is just some data, and we impose some axioms on this data, right? So here are the axioms. So the first, hopefully, is not so surprising. So each pair of points is contained in a unique line. I guess I meant to say each pair of distinct points here. Okay, so distinct points should be contained in a unique line. That just makes sense, right? We know if I have 2 points, I can draw the line between them. And then axiom B, this is very specific to projective geometry, which is that if I give you 2 lines, again, it should say 2 distinct lines, then they should meet in a unique point, right? So either they're kind of just 2 general lines and they'll just meet somewhere, or if they happen to be parallel, then they'll still meet, but at some point at infinity, okay? But what you notice about these, so axiom A is kind of very, it's sort of one of the axioms of Euclidean geometry. Axiom B is specific to projective geometry. But what you notice is that there's some sort of symmetry here, right? So pair of points meeting in a line, pair of lines meeting in a point. And what that means is that I can swap these sets P and L. So if I give you some sort of world of projective geometry, I can swap the points for the lines or the lines for the points, and these axioms will continue to hold because they're entirely symmetric under that operation. Okay, so this is sort of the axiomatic way of seeing projective duality in action. All right, so in any case, we know therefore that the lines of P2 correspond to points in P2, and I'll write kind of this square brackets L for the corresponding point. And what that means is that I can think of P2 also as a moduli space, right? I can think of it, it's a little bit confusing, but I can think of this P2 as the moduli space for lines in P2, right? So every point in P2 is parameterizing some line. All right, so now let's see what we can do with this. If I give you a curve in P2, I can look at all the lines in P2 which are tangent to that curve, right? So if I give you a general curve, then most of the lines won't be tangent to it, but some of them might be, okay? And for all the lines that are tangent to my curve, I take the corresponding point, okay? So by doing that, I get some subset of P2. So it's all of these points here, these Ps, which correspond to lines which happen to be tangent to my curve C, okay? So we write this C star and we call this the dual curve. And it turns out, it's not completely obvious, but it's not so hard to show, that this is also a curve. So if C was a curve, then C star is also a curve, okay? And moreover, if we know the equation for C, we can figure out the equation for C star for its dual. And so a special case of this, here's an exercise. This involves some sort of, multivariate polynomial algebra here, is that if we started with a conic, so if we started with a conic curve, then the resulting dual curve is also a conic, okay? And I've sort of written what the sort of algebraic content of that statement is here, okay? So this is something you can go away and think about for yourself. But if you take this on trust for the minute, then we can do something very interesting. So let's fix two conics in P2. And now we can build their dual curves, right? C1 star, C2 star. So remember, these are the curves that parameterize lines tangent to my original curves, okay? And what we just said, this exercise that I set you, is that these are also conics, okay? But then once we've done this, we can intersect these dual curves, right? And because we have Bezout's theorem, we know that these should intersect in 4 points, right? So there should be 4 points of P2 that are in the intersection of these two. But let's think about what this means geometrically. So C1 star, right? This parameterizes lines in P2, which are tangent to C1. And C2 star parameterizes lines in P2 that are tangent to C2. And so what this intersection is it's lines in P2 that are tangent to both C1 and C2, okay? And what we've just argued, using the theory of duality and using Bezout's theorem, is that there should be exactly 4 of these. And here there are, right? So I've got C1 and C2, and I've got these 4 lines, 1, 2, 3, 4, which are tangent to both. So you see, this is very, very similar to this kind of circles question that we had at the beginning, right? But here we've solved it in a completely different way, right? We've used the fact that P2 was some sort of, moduli space parameterizing lines, and then we've looked at how many lines were tangent to both, okay? And so this is kind of really setting out a blueprint for how enumerative geometry is done nowadays, okay? So here it is, right? So here's the blueprint. And as I say, it's easy with A, B, C. So step A is you start with some moduli space of things that you want to parameterize, okay? So in this case, we were looking at lines, right? So our moduli space was just P2, okay? And what we note is that this is finite dimensional, okay? So there's only finitely many parameters I need to parameterize these objects. Then what we do is we impose some conditions, okay? So in this case, we impose that I was tangent to C1 and tangent to C2, and we imposed 2 conditions because P2 is 2-dimensional. So we wanted to cut down to some finite number of objects, and then we want to count how many there are, right? So we imposed a tangency, and the way we did that in the previous slide was looking at C1 star and C2 star, so these dual curves, okay? And then finally, once we've done that, right, we've started with our moduli space, we've cut it down to finitely many points. Then comes the hard step, which is to find out how many there are, right? We need to count them. And in the last case, we found there were 4, but the reason we knew there were 4 was because we knew there was we had Bezout's theorem, right? We didn't really find them, not in any careful way. We just applied the kind of heavy, sledgehammer of Bezout's theorem to tell us the answer. Okay. So this is the general blueprint, and this is what people do still to this day, right? So this is how enumerative geometry really is done nowadays. All right, so with that in mind, let's come back to our original problem. So if you remember, we were looking at circles in the plane, and previously we were thinking about these as being defined by some center and some radius, but I'm going to take a more algebraic approach here, right? So a circle would be defined by some equation. It's a degree 2 equation, so it's a conic, but it has a specific form, right? So if you look at this equation that I've written down, you'll notice that firstly, there's no x times y term, so I've just set that to be 0. And also the coefficients of x squared and y squared are the same, yeah? So I have ax squared plus ay squared. So this is some special class of conics, right? Defined by equations of this form. I get 4 choices for these coefficients, right? A, B, C, D. And I'm thinking of these either as living in C2 or probably, as we've kind of already talked about, the correct way is to think about it as living in P2, okay? So we think of these as circles, okay? This is kind of bending the truth a little bit, right? Because really we're working in P2. These are really complex numbers, okay? But whatever circle means in the complex world, this should be it, right? From the algebraic point of view, we can think of these as circles, okay? So we're going to take that liberty here. Again, there's some drawbacks, which is that things are more uniform, but there's a benefit, which is also that things are more uniform, okay? So with this approach, we can try to parameterize all these conics, right? All the conics that look like this. So what's the information I have to give you? Well, I have to give you these 4 coefficients, right? A, B, C, and D, okay? And I don't want them, okay, so I shouldn't have all of these coefficients being 0, right? Because if they're all 0, then I just get the equation 0 equals 0, which definitely doesn't define a circle. But as long as they're not all 0, I'm kind of happy enough with that, okay? And then also, they're only well defined up to overall scaling, right? So if I multiply all of these coefficients by some number, I get the same equation. So I get the same circle. And so once again, the moduli space that I'm after is this quotient. So C4 minus the origin mod C star. So this is very similar to what we saw before, except instead of C3 minus the origin, I have C4 minus the origin, okay? So this quotient is what we call P3, okay? Yeah, here it is. So it's this quotient. So what is P3? Well, P3 is what comes after P2, okay? So you can kind of use your imagination to think about what that would mean. So the moduli space of these circles in P2 is given by this space P3, okay? And let's just say a few things about the geometry of P3. So the 3 kind of indicates that it's 3-dimensional, right? So we have these 3 parameters, which is actually what we saw right at the beginning anyway, right? So we had the center of the circle and we have the radius. Okay, now we're working over the complex numbers, but nevertheless, we're still seeing that we have 3 parameters. So just like with P2, right? So in P2, I could look at some polynomial equation and look at the curve that it defined, some solution set. So I can do the same thing here, right? So I take a polynomial. This is in the kind of coordinates on my P3. And if I have that polynomial f, I can look at its solution set and I get some subset of P3. But since P3 is now 3-dimensional, this solution set will be 2-dimensional because one equation cuts down the dimension by 1, okay? So these are 2-dimensional things living in P3. So they're not curves anymore, but they're hypersurfaces. So they're surfaces in P3. And the degree of one of these will be the degree of that polynomial. And just like we had in P2, there's a generalized Bezout's theorem for P3. So you'll notice here, we're now intersecting 3 things instead of 2 things. And that sort of makes sense, right? Because we're on a 3-dimensional space. And each of these things is 2-dimensional, right? D1, D2, D3. So every time I intersect, I'm cutting down the dimension by 1. So I go from, D1, it being 2-dimensional, to D1 intersect D2, which is 1-dimensional, and then to D1 intersect D2 intersect D3, which is 0-dimensional, and I can try to count the number of points. And it turns out that the answer is this product, okay? So it's a straightforward generalization of what we saw for Bezout's theorem. All right, so keeping this in mind, we can now try to answer our original question. So we have these 3 circles, right, sitting inside P2, defined by these equations. And for each of them, I can consider so for each Ci, right, I'm going to consider some set Di. So what this is going to be is it's going to be circles which are tangent to Ci, okay? And remember that the set of all circles C is P3, right? This moduli space. So if I look at circle C with this tangency condition, that gives me a subset of P3, okay? And it turns out that this is actually a hypersurface, so it's defined by a single polynomial equation in P3, and its degree is 2, okay? So I've set a few exercises in this talk, and some of them are easier than others, but this one is really not very hard, okay? So you can go away and check this for yourself, but this thing really is a degree 2 hypersurface. Okay, so given that, we can then try to answer our original question. So let's think, what was our original question? It was, how many circles are there which are tangent to C1, C2, and C3 simultaneously? And if we think about what that means, it's basically asking how many points are there in the intersection of D1, D2, and D3, right? So if I belong to all of these, that means I'm tangent to all the circles. And the answer, of course, is now going to be given to us by this generalized Bezout theorem, right? So the number of these points should be the product of their degrees. And we just calculated this. Well, I asked you to calculate it as the number 2. And so we get 2 times 2 times 2, which is 8. It's kind of funny because previously we also got this number 8 as 2 times 2 times 2. There were these binary choices of whether to be inside or outside. But this is really a different 2 times 2 times 2. It's really not the same. It's coming from Bezout's theorem and the fact that, you know, each of these is some degree of some hypersurface in P3. But either way, we get the same answer. And here we go. We're back at the same picture that we started with. Okay. All right. So thank you very much. I hope you enjoyed.